and we ended up with like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pulses here, right? And the same thing, 1, 2, 3, 4, 5, 6, 7, 8. So if you increase the M sub f, you would have more pulses. So your waveform would be basically having less harmonics. The other thing I wanted to mention, I'm sorry about that. The other thing I wanted to mention is that you look at this one. If you look at the sine waveform and the carrier signal, you see that the amplitude of the sine waveform is smaller than the carrier signal. What would happen if this sine waveform gets bigger, or like the amplitude of it gets bigger than the amplitude of the carrier signal? In that case, we would just like end up with one big pulse in the half cycle and then one other big pulse in the lower half, right? So like just like one pulse here and the other one like here, and then like in the output we just like have one pulse and one pulse. So that's actually called overmodulation. So if you look at here in the lower right part of the board, if MA is bigger than 1, we call this overmodulation, and we want to avoid it, right? Because then we would have a lot of harmonics. Instead of having 10 pulses for each half cycle, we only have 1, right? The same thing happens if you have if your sinusoidal wave has some DC offset, right? In that case, then like the comparator wouldn't do a good job, because like your sinusoid might be here, right? It's always going to be bigger than your carrier, so you always have high voltage. We don't VDC, positive VDC voltage. So like we don't want this happen. So we have to make sure that our sinusoid and the carrier basically are aligned, no DC offset. The other thing that we want to make sure, so basically the average of both of them should be 0. The other thing that we have to make sure is that our M sub A, which is our modulating index, is smaller than 1, right? If we do that, then we end up with a modulated signal like this. Now this signal has a fundamental frequency that we want, like has a fundamental component similar to this one, but it also has higher order harmonics, because it's not a sinusoidal. Like you remember from Fourier transform, this signal has a frequency, let's say if this is 60 Hertz, this signal, it's a periodic signal with the frequency of 60 Hertz as well. So it has, doesn't have any DC voltage because the average is 0, but it has a 60 Hertz component, 120 Hertz component, 180 Hertz component, and so on. Actually, like you would see that like it doesn't have second order harmonics, but or like even order harmonics, sorry. But it would basically have harmonics. But if you do the Fourier transform for this, you would find out that the fundamental component, call it V sub 1, basically this is the 60 Hertz frequency. If the frequency of our reference is 60 Hertz, has this formula, right? So it has the same frequency as our reference signal. This F is the frequency of the reference signal. Let me do it with red so that you know that it applies to this one. This is reference. This is carrier. Okay, and its amplitude is M sub A times Vd over 2, right? But this is the case if A is less than 1. Okay, so you would have higher higher fundamental component as you increase A, but you have to make sure you don't enter the overmodulation region, right? So in your notes, Dr. Jeff provided a very nice table that shows shows basically how harmonics changes like as you increase MA from 0 up to 1. So I definitely recommend that you guys like see that table. And the other thing I wanted to mention is as I already told you, if you look at this one, first of all, it's an odd function. It means like it's symmetrical. First of all, if you look at these two parts, it's symmetrical, and the same thing happens here. You remember that for an odd function, we have f of negative x is equal to negative fx, right? And so we have this feature. We also have the feature that this is gonna be symmetrical. Like you look at it like it's as if we mirror this. So if you do the Fourier transform for this one, you would find out that we only have odd order harmonics. It means that we have the fundamental component, which is the first component. We don't have second order, we don't have fourth order, sixth order, eighth order. We have third, fifth, seven. Actually, their values are small because nothing is perfect. But what we end up with, it's only odd order harmonics, third order, fifth order, seventh order, and so on. Okay, and as you increase the switching frequency, we can make the values of these harmonics smaller, right? And then basically we kind of shifting the harmonics. If let's say like our third order harmonic has a big amplitude, then if you improve the quality, then we can reduce this one. Then like we might have like a 9th order or 11th order harmonic, right? And the higher order harmonics are easier to filter, right? The higher order harmonics are easier to filter. We don't need to have like very big capacitive and inductive components, elements to filter them. So that's why like we want to make sure to do a harmonic analysis to have the fundamental components that we need. So if you need to have a certain voltage, let's say like you need to have 120 volt 60 hertz, right? So you want to make sure that your MA is such that you would get this 120 volt for your fundamental component. But if you calculate the RMS value, it's definitely going to be higher than this because you would have harmonics. You saw that actually in our lab for rectifier. Like one of the question was asking you that you expect to get like 120 volt or 208 volt. Why do you get like 230 volts? It's because of the harmonics. The other thing I wanted to mention is that, like if you increase the switching frequency, you get a smoother waveform. What's the drawback of that?